So as I mentioned, we're going to do a couple of sections in chapter 9, and then we will be done with the new material for the semester. So we have two concepts that we're going to learn about here to solve these systems of equations using matrices. So the first one, what we need to do is have a common understanding of what is a matrix and how do we do that. And so what I've put here for you is kind of just the standard definition. I'm not going to read it to you. You guys are quite capable, I am certain, of reading. So I really just want to, show you what that is, what it looks like, and how we can navigate with them, and how we can take these equations that we're given and turn those into matrices. Okay, and so in order to do that, we have to write these systems of equations in that standard form where we have x plus y plus z equals a constant. Okay, so this first problem, you can see that we have that in that format. And so when we want to look at this is really like saying I have 0x's plus 5y plus, is equal to 12. Okay. When I want to write that in matrix form, I just use the constants only, knowing that this is x, this is y, and this is my constant c, and we'll kind of just divide it with the line. Okay. And so my x in my first one is a 3. My y is a -1. My constant is 10. Okay. So in my second equation, my x is 0, my y is 5, and my constant is 12. So that is how we convert that system of equations into a matrix. Okay, any questions? Okay. So for problem number 2, you can see that we're not in our standard form. So we have to do that first. So we'll have to distribute this 3x to both of these pieces. And that's going to give me 2x plus 3x plus 3y equals 1. But we still have to simplify this portion here a little more to get us 5x. I'm going to write that in a different color. This right here becomes 5x. Okay. And so for our second equation, that gives us 6x minus 6y equal 14. I'm just moving the constant to the right-hand side instead of having it on the left-hand side. Okay. So now we have this in a format that we can quickly and easily turn into a matrix. So our x is 5 and our y is 3 and our constant is 1 for the first equation. And for our second equation, we have 6, -6, and 14. Okay. Question. Okay. For this next equation, let's just go ahead and rewrite it, filling in any of the missing variables with a 0. So we have x plus 0y plus z is equal to -1. Here we have 2x plus y plus 0z is equal to 5. And here we have 0x minus y plus z equals 3. So you see how we put those in, we arranged them X, Y, Z order. because we have to make sure that it's in the correct order before we build our matrix, or our matrix will not be correct. Okay? So my first equation, I have 1x, 0y, 1z, and -1 for my constant. My second equation, I have 2x, 1y, 0z, and 5 for my constant. And my last equation, I have 0x, -1y, 1z, and 3 constant. Okay? Any questions on how we transform our system of equations into a matrix? Okay. Now, what I want to point out here is, you notice this matrix has a negative, or not a negative, it has a 1 in that diagonal. So we have a 1 in the x position in the first equation, a 1 in the y position in the second equation, and a 1 in the z position in the last equation. Okay. So that really is, if I have a matrix, and so that is what we would call the identity matrix. Identity matrix, you have a diagonal of 1s and everything else is 0. Okay. And so this is really telling me that I have x plus 0y plus 0z is equal to -3. Okay. Well, when we write equations, we don't really write those zeros in, right? So we would just say x is equal to -3, y is equal to 0.05, and z is equal to 12. Okay. So essentially, if we were to solve this matrix and make it look like this identity matrix, we would get the solution to our problem, or to our system of equations, whatever those might have been. Okay. So in a similar format, then that means, that this one is -8x plus 7y equals 113. Okay. And 2x, we don't need to put plus 0y, is equal to 1/3. Okay. Question. Okay, so here is our, when we do elementary row operation, okay, so this is how we can do math on these matrices to reduce them down to that identity matrix so that we can end up with the solution. Okay. We'll actually take it to the identity matrix in section 9.2. In this section, we're actually just going to get the diagonal here with the zeros under here, and we don't care what these numbers are. Okay. And so that's when I say we have two different concepts tonight. That is it. So in section 9.1, we're only going to get the lower half of the triangle to be zeros. But in section 9.2, we'll get the diagonal of 1s and all other spots to the left of that line, which represents the equal sign in the equations, we'll get to be 0. And we'll do that by performing row operations on the row. Okay. So there's 3 basic operations that we can do. We can interchange 2 rows, because remember, we want that very first position to be a 1, right? So if I have an equation that already has x as a 1, why wouldn't we want to just swap those 2 rows instead of doing some long, laborious calculation to get that 3 turned into a 1? Okay. So that's what we have here. If we, so this is really just saying And when I write it, I'll write it row 1, replace, I'll put a row 1, replace row 2. And because I'll write out all of these each step of the way to help guide you guys into what we are doing as we perform these row operations. So what would that look like? It then gives us a matrix. We're just trading places, so it becomes 1, -2, 10, and 3, 2, -5. So that's all we did is trade places with those two rows. Okay. It's the most basic operation that we can do. Okay. Question. All right. This next one is if we didn't do that and we wanted to get this, our first step is to make sure that that first position here is a 1. And so if we didn't swap places with them, we would have to do something else. And this says row 1, but we're actually going to change that. Hang on. This should be row 2. Sorry. We're going to multiply row 2 by, actually, there's lots of different ways that we could do this. So, in this one, we're not reducing it at this point. This will just show you more the effort. So if we do, as it says, multiply row 1 by 3 and replace row 1. So that would be, for the first one, that would be 3 times 3 equals 9. So that becomes a 9 right here. And 2 times 3, or let's put the 3 first because we're doing 3 times row 1 is a 2, so that gives me a 6. And 3 times -5 gives me -15. Okay? And so that's the only operation that we did here, and we copy row 2 exactly as it is because we didn't perform any operations on it. So it would leave us with a matrix that looks something like that. Okay? Questions? And this last one says if we do 2 times row 1, add it to row 2 and replace row 2. That's kind of what that arrow is you can enter. So if it's a single arrow, it's saying whatever I do in this operation, I'm going to replace it over here. And so this one becomes, so we take 2 times row 1, so 2 times row 1, add it to row 2, and replace that. So I get 2 times 3 is 6 plus 1, that is 7. So I'm replacing the 1 here with the 7. Okay. We're not doing any changes to row 1, so we could actually just copy that straight down. Okay. And now we do our second element. So we have 2 times -2 plus, so 2 times it's a +2, sorry. 2 times 2, right? Plus what's in row 2, that's my -2, equals what? So 4 minus 2 equals 2. So we're replacing this, and that becomes a 2 down here. Okay. So now we do 2 times row 1, 2 times row 1, plus row 2. That gives us a negative 10 plus 10 is a 0. And so that would replace that here. Okay. Question. All right. So after we write this augmented matrix down in this in the echelon form. So remember, when I said we're only going to get the bottom portion of the matrix to where it has the zeros, then so because we're only going to do that, this is what we would call the Gaussian elimination method. Okay. So it's 3 steps, right? We're going to write our augmented matrix for the system. We're going to use our row operations to get it where we have a 1 in the first column, first row, a 1 in the second column, second row, and so forth, and then just zeros underneath it. Okay. So we're not concerned at this point in getting the zeros above and below that diagonal of 1s, just below. Okay. And then we'll use back substitution, kind of a mix of how we did last week's problems to solve out the rest of the problem. Okay. And then, like I mentioned before, in the second section, that's when we'll get the zeros above and below, and we'll be finished with it, have a final solution, and not have to do any backward substituting. And that's what is going to be called Gauss-Jordan. It's going to be the Gauss-Jordan elimination method. Okay. All right. Any questions so far? All right. Let me make sure. All right. All right. So what we have down here on the bottom is we have an example. So we want to first take and write this problem in the correct format for our equation. So this one gives me 3x plus 3 equals 5y plus 4. We want to move the 3 to this side and the 5y to this side. That's going to give me 3x minus 5y equals 1. Okay. So when we look at building our matrix here, our first one is 2, 3, 7, right? So that's 2x plus 3y equals 7. My second equation here is going to be 3, negative 5, 1 to give us that second equation. Okay. And if we're going to write this in, so we've written it in standard form. Now we're putting it in an augmented matrix. That's what the matrix here looks like. And now we want to perform row operations to give us the diagonal of 1s and then get the 0 underneath it. So in an effort to not undo things that we have already done, we want to, you don't want to get a 1 here first, because then you may undo it when getting a 1 here. So we kind of want to work in a process to make sure that we don't undo any of our problems. So I'm going to just do this here. build us out another matrix. And since we're going to be changing row 1 only, I'm going to copy row 2 over because we're not making changes to it. Okay. So what can I do to that number 2 to make it a 1? Thinking back to the 3 things that we can choose from, right? I can't switch it with row 2 because row 2 doesn't start with the 1, so it wouldn't help me, right? And so probably the easiest one would be the second one, which is to multiply a row by a non-zero constant, okay? So could I multiply it by 1/2 and replace it, right? So what is 2 times 1/2? That gives me 1, right? So that would give me a 1 here. So 2 times 1/2 gives me 1. 3 times 1/2 gives me 3/2. And 7 times 1/2 gives me 7/2. Okay? Any questions on that? Okay? I'm going to just build our next piece down here. Okay? So now our next step is we want to get a 1 in this spot right here. So if we're going to get a 1 in that spot, we're not doing anything to the first equation. So that is 1 3/2, 7/2, and we just leave it at that. So what do I need to multiply -5 by to get that to be a 1? Okay. And so I can, so there's 2 different ways that you could go about this. You could get the 1 here, or you could get the 0, right? Either way is okay to do. Okay. Um, so for this example, I will do the diagonal ones first, and then we'll come back and get that 3 into a 0. In a future one, I'll show you that it also works if I do 1 in this spot, then I get the zeros underneath it, and then I move to the next diagonal and so forth. Okay. But if I jump around outside of moving from left to right or the zeros, then I can undo and end up having to do a little more work to reduce that problem out. So in this one, I can multiply by a -1/5 of row 2 and replace row 2. Okay. So that would give me a -3/5. This would give me a +1, and this would give me a -1/5. Okay. Question. Okay. So for this next step, we want to get this right here to be our 0. Okay. So how can we do that, right? And so usually the easiest way is to do the opposite sign of this times the 1 and then add them together, right? So if I did positive 3/5 of row 1, and I'll show you how this is actually going to undo doing our 5, and that's in how we end up having to do extra steps. So if I do 3/5 times row 1 and replace and add it to row 2 and replace row 2, Okay. So what does that look like? So when we do this, we have 3/5 times row 1 plus row 2 equals positive 3/5 minus 3/5. That gives us our 0. I'm going to go ahead and write row 1, 3/2, 7/2. Okay. Now we have 3/5 row 1. Now we have 3/2, right? Plus row 2 equals, so that gives me 9/10 plus 1, or 10/10, right? So that gives me 19/10. Okay. So when I do that, you see I go 0 and now I have 19/10. And so I no longer have my 1 in that spot, right? Okay. So it's okay. It just means we have one more step we have to do before we're finished. And then I'll show you what it would look like if we had went and if we had done this first, this second, and then this third, right? How does it look different and how we have less steps? Okay. But we're going to finish this out this way just to show you how we get that. Okay. Now for our last one, we have 3/5 times row 1, which is 7/2, plus negative 1/5. Okay, so that is 21/10 minus, this is the same as 2/10. So that equals 21 minus 2 is 19/10. Okay. So now we have to do one more step. Okay. So we're still keeping row 1 the same. But now we want to, once again, I'm going to do it in blue again, because we want to get that 19/10 back to a 1. Okay. So just multiply by its reciprocal. So that is 10/19 times row 2, replace row 2. So now I could say 0 times 10/19, that still equals 0, right? 19/10 times 10/19, now that equals 1. Okay, so now we keep our 0. Now we have a 1. And we have it again, 19/10 times 10/19. Actually, I should have wrote it in the other direction just because we have 10/19 first, times row 2, which is 19/10. It doesn't matter at all if you guys write it in that way. I'm writing it just so if you come back later and you're like, wait, where did that come from? You can just reference the equation that we have up there and see that. Okay. So now what this is showing me then is that we have x plus 3/2 y equals 7/2, and we have that y equals 1. Okay, so we could plug 1 back up into this equation here, and we get x plus 3/2 times 1 equals 7/2. So that would be x equals 3/2. Let's move it to the other side. So 7/2 minus 3/2 equals 4/2. So x is equal to 2. So our solution here would be 2, 1. Okay? Question. So on future ones, we'll do 1, 2, 3, right? Just so that we don't have as many steps to do. We can eliminate, had we done that, we would have eliminated this piece right here. Okay. And so, but I want to show you that even if you do things out of order and you have to do things twice, which we did here, right? We did that twice, you can still get it reduced. Okay. Question. Okay. So let's look at a 3 equation matrix. Okay. So what I want to do is give you guys about 1 minute to set this up on your paper yourself, so that if you have questions that you can ask them now instead of when you get to your homework and you're not understanding. Okay, so take a minute to set up your matrix. All right, so again, make sure that our x's are in column 1, y's in column 2, z's in column 3. So our first equation would be 2, -6, -1, 7. We would have 1, 2, 1, 0, and 1, 4, 2, -3. Did anybody get something different, or does anyone have questions about how we took those systems of equations and wrote it in an augmented matrix? Okay. So again, in this case, remember, um, we can switch rows and whatnot. All I'm going to do is I want to just move this to the bottom, right? So I can say that I want row 1 and row 2 to switch places. But then I also want to take row 2 and switch it with row 3. I don't have to. I could have just switched one, but so ultimately I'm changing all of the rows up, right? So row 2 goes into the first slot. So 1, 2, 1, 0. And row 3 goes up into the second row. So that's 1, 4, 2, -3. And then we put the first row down at the bottom, 2, -6, -1, 7. Again, we could have just interchanged row 1 and 2, or row 1 and 3, and left that and did it in a different order. It doesn't matter at all how we shuffle them up. I'm trying to just show you there's lots of different options here when you start building these out and doing it for yourself. Okay, question. Okay, so now what we want to do is we want to get those zeros in place, right? So we want this and this to be 0. I'm going to just do it, excuse me, one row at a time. In the future, you could do both of those at the same in the same step, but I'm going to solve it out one at a time to kind of help you focus in on that. So we're going to be leaving row 1 and row 3 exactly as they are. So let's just copy them down. 1, 2, 1, 0, and 2, -6, -1, 7. So we're leaving those exactly as they are. But we need to get that 1 to be a 0. So how do we do that? If I do negative row 1 and add it to row 2 and then replace row 2, I would achieve that, right? Because I have negative row 1, which is, so -1 plus 1 equals 0. Then I have -2 plus 4 equals 2. And then I have -1 plus -1 equals 0. Hang on. 0 to -1 plus 2. Hang on. I was on the wrong row. Sorry. Plus 2 equals 1. We put a 1 in here. And then we have -0, which it's really just 0, plus 7, not 7, we're on row 2, plus -3 equals -3. Okay? Question. All right. So now what? Now we want to get a 0 in this spot. Okay? We could do the same. So now again, we're just doing -2 of row 1, right? Because -2 times 1 is -2 plus 2 is 0. So we'll add it to row 3 and replace row 3. Okay, so we're not changing rows 1 or 2. So we'll just copy those down exactly as they are. Okay. So now we have -2 times 1 plus 2 equals 0. We have -2 times 2 plus a -6. So that's -4 minus 6. That gives me a -10. We have -2 times 1 plus -1. So that's going to give me a -3. And -2 times 0 plus 7 equals 7. Okay? Questions? Okay? All right. So now we can go for either one of these two. Let's do the 10. Let's make the 10 a 0. Okay. So how do we do that? So we know that rows 1 and 2 are not going to change. We copy those down. Our row 3, if we want to make that a 0, how could we do that, right? So we could do 5 times row 2, add it to row 3, and replace row 3. Okay. So we have 5 times 0 plus 0. That's still 0. See how we don't undo the math we've already done? So 5 times 2 minus or plus, let's keep it in the format of plus -10. That gives me a 0. And we have 5 times 1 plus -3. That's going to give me a 2. And then 5 times -3 plus 7. That's going to give me -15 plus 7 is -8 for that slope. Okay. Questions? Okay. Now we want to get this one right here to be our 1, right? So that is going to be 1/2 row 2, replace row 2. So if you think about that, 1/2 times, well, let's write our first and 1, 2, 1, 0, and 0, 0, 2, -8. So 1/2 times 0 is still 0. 1/2 times 2 is 1. 1/2 times 1 is 1/2. And 1/2 times -3 is -3 halves. Okay, any questions? The last thing that we need to do to this matrix here is let's make this right here a 1 as well. And so to do that, we do 1/2 times row 3, replace row 3. Okay. So rows 1 and 2 are staying the same. So we just put 1, 2, 1, 0, and 0, 1, 1/2, -3 halves. Okay. So 1/2 times 0 is 0. 1/2 times 0 is 0. 1/2 times 2 is 1. And 1/2 times -8 is -4. Okay, so now you can see change to a highlighter. You can see here then that we have this diagonal here of 1 and everything below it is a 0. Okay. And that's what we were aiming to get. That was what we were trying to achieve. We have done that. So now let's just write our equation out. This gives me that x plus 2y plus z equals 0. I also have that y plus 1/2 z equals -3/2. And I have that z is equal to -4. Okay. So I can plug z into this equation, right? And I get that y plus 1/2 times -4 equals -3/2. So that gives me that y minus 2 equals -3/2. If I add 2 to both sides, I get that y is equal to, that would be the same as adding 4/2 over here if I'm adding 2 to both sides. So that would give me y is equal to 1/2. Okay. I can plug that and z up into this equation like we did last class period, right? And I get that x plus 2 times y plus -4 equals 0. So that gives me x plus 1 minus 4 equals 0. Okay, so x, sorry, I ran out of room down here. So that is x minus 3 equals 0, or x equals 3. Okay, so the solution then to this system would be 3 1/2 -4. Okay, question. If you did the same exact process that you learned last week by using the substitution and addition methods to eliminate things, you would get the exact same solution to this problem here. Okay, question. All right, so as I mentioned, if we write an augmented matrix in, so the previous one we did is what we just call row echelon form. If we write it in reduced row echelon form, that is when we get the Gauss-Jordan elimination method. Okay, so we're going to come back over here. We're going to just snag this piece of the matrix and copy it, paste it over here on the next page. I'll even leave that diagonal in there so that you can, if you come back and look at these, you'll be like, oh yeah, that's from the previous page. We're just carrying it forward. So now, instead of doing all of this calculation stuff that we did right here, we're going to get zeros in the top half of this. We're going to get zeros up here in this portion. Okay, so we just want to get those turned into 0. All right, so how do we do that? So the first one we can do is, let's see. Let's do, let me build our matrix. So let's look at our row 1. Okay. So in row 1, we have a 2 in that second slot. In our row 2, we have a 1/2 in the third slot. You can see we don't have any reductions to our row 3. That's not necessary, right? And so there's multiple ways you could do this. Do you want to get your zeros here first? Do you want to get your 0 here first? How do we want to do that, right? So for this one, let's go ahead and start with this one. Okay. Sorry, I have it. There we go. Let's start with this one. So in order to do that, I am going to keep my first and third rows. So we have 1, 2, 1, 0, and we have 0, 0, 1, -4. Okay. So if I want that 1/2 to be a 0, then I can take negative 1/2 of row 2, take negative 1/2 of row 2 and make that, we take negative 1/2 of row 3, add it to row 2 and replace row 2. Okay. So we have negative 1/2 of times 0 plus 0, still 0. Okay. I have negative 1/2 of 0 plus 1, still 1. I have negative 1/2 times 1 plus 1/2, that gives me 0. Okay. Negative 1/2 times -4 minus 3/2, or let's do it plus parentheses -3/2. So that's going to give me a positive 2, which is the same as 4/2 minus 3/2. So that's going to give me a 1/2. Okay. Any questions so far? And that actually is starting to line up with, we already determined that y is going to be 1/2, right? Okay. All right. So now what do we want to do? Now we want to get, let's get this one right here as a 0. Okay. So that means we're changing row number 1. So row number 2 and row number 3 do not change. Now we want to how do we make that 2 0? If we multiply -2 times our row 2 and add it to our row 1 and then replace row 1, so that's going to give me -2 times 0 plus 1 still equals a 1. -2 times 1 plus 2, that gives me a 0. a -2 times 0 plus 1 equals 1. And a -2 times 1/2 plus 0 gives me a 1. I mean, a -1 because we have that -1. Okay. Everybody see that? Any questions? Okay. So now we want to get this one here to be a 0. Okay. So now we want to do negative row 3 added to row 1, replace row 1. So row 2 and 3 are staying the same. So we have 0, 1, 0, 1/2, and 0, 0, 1, -4. Okay. So negative row 3, which is a 1, plus row 1 equals 0. Oh, sorry, I skipped already to the third element. Let's start in the first one, sorry. Negative 0 plus 1 is still 1. Negative 0 plus 0 is still 0. Negative 1 plus 1 is 0. And negative -4 plus -1 equals 3. So we get that x equals 3, y equals 1/2, and z equals -4. And that is exactly what we came up with here when we did it that other method, where we only took it halfway. Okay. So when you take it halfway and then use equations to solve the rest, this is what we call Gaussian elimination. Okay. That's why you'll need to know this difference on the exam. So when it says to do Gaussian elimination, you'll take it down to this, and then you'll use equations to solve it out. For the problem that says to do Gauss-Jordan elimination, you're going to take it all the way, and you'll already have your solution at the end. Okay? Question. All right, so one more. This is saying Gauss-Jordan. That means we want to take it all the way to complete the identity matrix so that all we have is the diagonal of ones and everything else is 0. Okay? So for this one, I will do a couple of things in one step sometimes to just give you guys more examples, but not take a lot of time just rewriting the matrix. Okay. And to show you that you can also incorporate multiple steps into one piece. All right. So the first thing, though, we do need to do is let's build it. So we have 1, -6, 8, 7. Then we have 2, 3, 1, -1. And we have 5, 9, -17, -4. All right. So for the first one, We want to get a 0 here and a 0 here. Okay, so I'm writing it in two different colors to just kind of help you draw your eye to that. So that means that number 1 is staying the same. So we have 1, -6, 8, 7. And so the first one we'll do -2 times row 1, add it to row 2, and replace row 2. So when I do that, I get -2 times 1 added to 2, I get a 0. Okay. And the second one, I get -2 times -6 gives me +12 plus 3 is 15. -2 times 8 is -16 plus 1 is -15. -2 times 7 plus -1 gives me -15. Okay. For the bottom row, or row 3, we'll do -5 times row 1 added to row 3, replace row 3. Okay. -5 times 1 plus 5 is a 0. -5 times -6 plus 9 is 39. -5 times 8, -40 minus 17, -57. -5 times 7 is -35, plus -4 is -39. Okay? Any questions? Okay? So for this next one, we're just going to get this 15 here to be a 1. And in order to do that, it's just 1 over 15 times row 2, replace row 2. Okay? So we'll copy down row 1, which is 1, -6, 8, 7. And row 3, which is 0, 39, -57, -39. Okay? So 0 times 1/15 times 0 is still 0. 1/15 times 15 is 1. 1/15 times -15 is -1. And 1/15 times -15 is -1. Okay? All right. Any questions? Now let's make this 39 a 0. Okay? So we just need to change leave row 1 and 2 alone. So we'll copy those over. And 0, 1, -1, -1. Okay? So in this problem, we're really just looking at making that a 0. So it'd be -39 times row 2 added to row 3, replacing row 3. So that's going to stay a 0. -39 times 1 plus 39 is a 0. -39 times 1, that's +39, minus 57 is a -18. -39 times -1 is +39 minus 39, so that is a 0. Okay? Questions? Okay. So now what do we want to do? Let's get this right here as our 1. So we're going to keep row 1 and 2 the same. So 1, -6, 8, 7, 0, 1, -1, -1. Okay. So -1/18, because a negative times a negative will make that a positive of row 3, replace row 3. Okay. So anything times a 0 stays 0. -1/18 times -18 is a positive 1, and anything times 0 stays 0. Okay. Question. Okay. So for this next one, we can let's do 2 things at once. Let's do let's get both of those as zeros. That means we're just leaving row 3 alone. Okay. And so for the first one, we would have -8 of row 3 added to row 1, replace row 1. So that's going to give me anything, the zeros, and see how that keeps these from changing anything, because anything times 0 is still itself. I mean, it's still 0, so then when you add it to the previous line, it stays itself. So this one we have 8, -8 times 1 is -8 plus 8. That gives us a 0. And when we do the something times 0 is still 0, so this will remain a 7. Okay. For the second equation, we can just say, let's take row 3, add it to row 2, and replace row 2. So that's going to keep us at 0, 1. Now I have 1 plus -1. That's a 0. I have 0 plus -1 is a -1. Okay. So the last thing that we have here is to let's get this -6 into a 0 as well. Okay. So the second row stays put, 0, 1, 0, -1. Third row as well. So 0, 0, 1, 0. Okay. So what is that equation that we need? Make that a 0. That would be 6 times row 2 added to row 1 and replace row 1. So that's going to give me 1, 0, 0, 7. So that tells me then that x equals 7, y equals -1, and z equals 0. Oh, sorry, this is not a 7. This is a 1, because 6 times 0 plus 1, yeah, 7. Oh, we did it times row 2, so it's negative. Sorry. 6 times -1 is -6. -6 plus 7 is a 1. So x equals 1, y equals -1, and z equals 0. And we could actually plug that back into each of the 3 equations and see that it solves out correctly. But solving it back, that is not part of the requirement for the coursework, like in what you'll have to do in the ALEC. But if you want to check your answers, you're welcome to do that. Okay. All right. Any questions about Gaussian elimination, or Gauss-Jordan elimination? All right, so let's take a 10-minute break. It is 7:45, so let's come back at 7:55, and we'll talk about the last section where we look at inconsistent system and dependent equations, what that means, and how that would look in our matrix as well. Okay? All right, so 7:55, I will see you back here. All right. So it is 7:55. So let's go ahead and finish out this section. So as I mentioned before break, this section really is looking at inconsistent systems and dependent equations. So if you remember from last class period when we talked about something that was inconsistent, that would be if we solved it down and got something that said 2 equals 7. That's a false statement, so that would be what we would call an inconsistent system. Same thing applies for our matrices as well. And remember, dependent equations, they're really lines that are parallel to each other, or if we're in a three-dimensional space, they have all those points are in common. So it would be like the entire plane is on top of the other plane. It's just a multiple of it or something similar to that. Okay. So that's really all this first page here is telling us, that when we have something that is inconsistent, then we have no solution to it, right? If we have something that's dependent, it means it intersects in all places. Okay. So when we look at this system here, we can see that for the first one, we have x is equal to -18. The second one, we have y plus 2z equals 6. And z equals 3. Okay. So when we plug those in together, right? If I want to plug this into my previous equation here, I get y plus 2 times 3 equals 6. So y plus 6 equals 6. So y equals 0. Okay. Therefore, the solution then to this set would be x equals the -18, y equals 0, and z equals 3. So that had a solution, right? Now let's look over here at this other example. Let's say that this, instead of being z equals 3, that we had this 0 here, right? So we still have x equals -18, y plus 2z equals 6. But now we end up with this thing that says 0 equals 3. Well, this right here is a contradiction, right? Excuse me. Okay, so it's a contradiction. So that tells me that my system is inconsistent and there is no solution. Okay. Question. Okay. So as I kind of mentioned on the previous slide about the dependent, really that is, there's an infinite number of solutions. It means that every value that we choose is going to be, there will be a solution for all 3 of the equations. Okay. All right. So let me see. Okay. All right. So let's just try and solve this out a little bit. First, we'll write it into an augmented form. So we have 1, -2, 1, 5. Okay. 3, 1, -4, 1. 2, -4, 2, 10. Okay. And we want to get this to where let's just reduce this first. We have a 1 already in the first. So let's work on getting zeros in these two. Okay. Let me do them in 2 different colors again, just to help you guys as we're working through these. Okay. You can see the different equations. Okay. All right. So first row stays 1, -2, 1, 5. With the first equation, let's do -3 times row 1 added to row 2, replace row 2. So that's going to give me -3 times 1 plus 3. That gives me my 0. -3 times -2 plus 1 gives me 7. -3 times 1 plus -4 gives me -7. -3 times 5 is -15 plus 1 is -14. For our third row, that's going to be -2 times row 1 plus row 3, replace row 3. -2 times 1 plus 2 is 0. -2 times -2 is 4, minus 4 is, or plus -4 is 0. -2 times 1 is -2, plus 2 is 0. -2 times 5 is -10, plus 10 is 0. Okay. I want to point that out here. This here is what we would call identity, because 0 does equal 0. Okay. But because we have that a row of all zeros, it really just means that our first equation and our third equation are multiples of each other. And when we look at that, we can see that that third equation is really just 2 times the first equation. Okay? Question. Okay? So now we want to get this 7 here as a 1. So that is really just 1/7 row 2, replace row 2. So our row 1 and 3 stay the same. So 1, -2, 1, 5. And then our identity, which is all zeros. Okay. 0 times, or 1/7 times 0 is 0. 1/7 times 7 is 1. 1/7 times -7 is -1. And 1/7 times -14 is -2. Okay. Question. All right. So now let's just do one more step. let's do this right here as a 0. Okay. Because we don't, and the reason we're doing this is because we need to eliminate that z because we don't have a z equals something. So we'll try to get rid of that so that we could then do mathematics to help us come up with a generalized equation. Okay. So to do that, we can do our row 2 plus row 1, replace row 1. I'm going to scoot this stuff up just a little bit to have more room. Okay, so row 2 and row 3 are going to stay the same, so we'll copy those over. Row 1 is going to stay, this is 0 plus 1 is 1. 1 minus 2, 1 plus negative 2 is negative 1. And negative 1 plus 1 is 0. Negative 2 plus 5 is 3. Okay. I'm going to copy this over onto the next screen. Right here. Because really what we're looking at here is we already know that because we ended up with that 0 identity equation on the bottom, that we have 2 lines or 2 planes that are either parallel, right? Like all the points in one, they're not parallel, they're like the same, right? They're the same plane, just a multiple of each other. And then we can write that kind of in a different way. So in the first one, let's get our excuse me. This is, we have x minus y equals 3. In the second equation, we had y minus z equals negative 2, right? And so what we could do is rewrite this in terms of where our variable is on one side and our y is on the other. All of our variables, x's and y's on the left, x's and z's on the left, y on the right, because that's what both equations here have in common. So we could rewrite this as x is equal to y plus 3. It's the same thing, right? Similarly, we could rewrite this one to say that z equals y plus 2, right? And so if we think of this in terms of how we wrote our some of our things yesterday or last class period, where we have the general solution, then our x is equal to this y plus 3, our y is just itself, and our z is y plus 2. And that's going to hold true for all y when y is a real number. Okay? Question. Okay? So now we have another example here. Let's go ahead and write this into our matrix. Okay, so we have negative 15, negative 5, 40, negative 30. Then we have 3, 1, negative 8, 6. And we have 2, 2/3, negative 16/3, and 4. Okay. So in this case, let's look at how we can show that this system here is all the same equations, right? So if I did my first equation by 1/5 of row 1, replace row 1. Let's do our second equation as, let's just do negative row 2, replace row 2. And our third equation, let's do negative 3/2, row 3, replace row 3, right? So we would eventually find out that these are all one equation, but I'm showing you here in just one step. Okay. Okay, so the first one would give me 1/5 of negative 15 is negative 3, 1/5 of 5 is negative 1, 1/5 of 40 is 8, and 1/5 of negative 30 is negative 6. Okay. Negative, we're just changing the sign on all of our equations in the second row because it's just multiplying it by a -1. So that becomes negative 3, negative 1. I mean, positive 1 because it was, yeah, negative 1, positive 8, and negative 6. See how that's already looks exactly like the equation above it? When we multiply the bottom one by negative 3/2, we get negative 3, 2/3 is, 2/3 times negative 2, negative 3/2 gives me a negative 1. This gives me a positive 8 and a negative 6. So you can see here that we have all the same equations. They're all the same, right? And in its simplest form, that is, we have negative 3x minus y plus 8z is equal to negative 6. Okay. So we could write this system and we could say that we could write it as x, y, z, such that negative 3x minus y plus 8z is equal to negative 6. So that's one way we could have written it. Okay. Or if we wanted to make it to solve it for x, right? We could have, if we had solved this for x, that would have been negative 3x equals y minus 8z minus 6. And then we could divide everything by negative 3, right? So that gives me x equals if we want to, so we're solving it in terms of that. So x, divide over here everything by negative 3. So that gives me negative 1/3 y minus 8/3 z. Well, actually it becomes plus 2, right? If we divide everything by that. And so we could have said, well, we could have written it everything in terms of a different variable, right? And so then we could have said, we could have written it in a different way. Probably the easiest way here is that you'll want to just leave it in the X, Y, Z, and then the formula. But again, if we rewrote it in terms of Y, right? Say we had rewritten it in terms of Y, then we could have said Y is equal to negative 3X plus 8Z plus 6, right? And so, or we could have written it in terms of Z, and that would have been a different, all we do is solve for Z, and do it how we did last class period, when we're looking at the general form. Okay, question. Okay, we have one more example. So this one again, let's write our matrix out. We have 1, -5, -5, 1, 6, -30, -1, 6, 2, -1, -10, 2. Okay, so let's do like we did in the past. Let's get this one as a 0 and this one as a 0. So that's going to give me -6, row 1, added to row 2, replace row 2. And this one's going to give me -2, row 1, plus row 3, replace row 3. So that means row 1 is staying the same. So we'll copy it down. 1, -5, -5, 1. So our second row then is -6 times 1 plus 6. That's a 0. -6 times -5 is 30. 30 minus or plus -30 is a 0. And -6 times -5 is -30. I mean, it's positive 30 minus 1 is 29. And -6 plus 6 is 0. Okay. -2 times 1 plus 2 is 0. -2 times -5 plus 1 is 9. -2 times -5 plus -10 is 0. -2 times 1 plus 2 is 0. Okay. So in this case, let's do a couple of things here. Because of this, let's just swap rows 2 and 3, because that gives us that 0 already, right? So let's just take row 2 and exchange it with row 3. So we're just swapping them places. So row 1 stays the same. 1, -5, -5, 1. And we're switching these places. So 0, 9, 0, 0, and 0, 0, 29, 0. Okay. And now let's just in one step, we can get each of those to be ones. So let's make that a 1. That's going to be 1/9 row 2 replaces row 2. And 1/29 row 3 replaces row 3. So row 1 stays the same, 1, -5, -5, 1. And so this becomes 0, 1, 0, 0. Okay. And this one becomes 0, 0, 1, 0. Okay. So what we have here now, we have x minus 5y minus 5z equals 1. We also have that y equals 0. We also have that z equals 0, right? And so we get here, though, that when we plug in 0 and 0 into here, right? When we plug 0 in for y and 0 in for z, we actually get then that, so when we plug those up here into this equation, we get x minus 0. So basically we get x equals to 1, right? And so if you were to plug that into any of those equations, so you don't get at any point in this, you don't get a 0 equals 0. And at no point in this do you get a 0 equals some other value besides 0. So we don't have any dependencies and we didn't have any inconsistencies in this one. So we could say that x is 1 in this case and y and z are equal to 0. Okay. And if you plugged those values into any one of these given equations, you would see that that holds true. Okay. Question. All right, that is all of the material, not just for tonight, but that actually concludes all of the new material for this course for the semester. So just to recap, at the end of this week, so next Monday, all homeworks are due. 11:59 p.m. on Monday, 1 week from tonight, is the last time to turn in any of the Alex homework. It is the last time that I will get a report from Alex at midnight on next Monday to tell me the status of where you were on each of those homeworks. Please don't ask me to extend that because I do have to download it. I have to process all the grades. And then when you guys do have your final exam, I will have those graded within 2 days, grades in the grade book, and ready to post to the registrar. So the way moving forward from the rest of this semester, next class period, we will meet and go over exactly what you should expect to see on that comprehensive final exam. Remember, if you didn't do as well on one of the first 3 exams as you preferred, if you perform better on the final exam, I will drop your lowest regular grade exam and replace it with the grade that you got on your comprehensive final. So say you were sick or whatever and couldn't take test 2, so you got a 0. I will replace that 0 with whatever grade you get on your final exam. Okay. Also, if you didn't miss an exam and say you just scored a 75 on exam 1, but an 80 on the final, I'll drop the 75 and replace it with an 8. Okay. So the final, because it's comprehensive, the final has to stand for its final grade. You can't replace the final exam. The only one that can be replaced is one of the first 3. And the way I'm able to get around that is because the final exam is comprehensive. Okay. So, but you have the final exam will stand as its own grade, and it can't be replaced. Okay. Any other questions? All right. If you guys don't have any other questions, that's all of the material I have for you. Feel free to shoot me an email if you come up with any questions between now and next Monday. If not, on Monday, we will do our exam review, and then you should be prepared for the final. All right. You guys have a good evening.